Hi, and welcome to Rosie's STEM. Today, we're going to be unraveling the mysteries of hypothesis testing and those elusive p-values. Hypothesis testing and p-values may seem like daunting topics in statistics, but by the end of this video, you'll have a clear understanding of what they are and why they matter. But before we dive in, let's lay a solid foundation. If you're new to statistical inference, please check out my previous video where I explain the concept of statistical inference and the definition of a statistic. The link is going to be right here. In essence, statistics help us glean insights from data, and that's what hypothesis testing is meant to do. Now, let's talk about hypothesis testing. It's a pivotal tool for making informed decisions based on evidence from data. Imagine I have a sample of 10 students from my class, and I believe that they've rated my class very highly in their evaluations. In statistical terms, my belief about those students' ratings is a hypothesis, or a proposed statement about a population or a phenomenon. In hypothesis testing, we establish two hypotheses. The null hypothesis, which we often call H0 or H0, and the alternative hypothesis, which we denote with HA or H1 to be similar to that H0. The null hypothesis represents the status quo, or a situation where there's no effect, no change to what we're currently doing. So let's say we're testing a new drug for disease X. The null hypothesis suggests that there's no improvement compared to whatever the existing drug is. The alternative hypothesis is usually what we're interested in testing, whatever we care about. In this case, it would be the belief that our new drug is going to be more effective than whatever we're currently using. Importantly, our two hypotheses, the null and the alternative, need to cover all possible outcomes. So in this case, the new drug is not better than the existing drug, and the new drug is better than the existing drug are the only two possibilities. So this ensures that our test is valid and rigorous. So here's how hypothesis testing unfolds. First, we have to collect data to test our hypothesis. Now that might be data on how well a drug works, or data on how my students are rating a class. Then with that data, we calculate a test statistic. This sounds more complicated than it is. You're just computing a statistic that summarizes the data's relationship with my hypothesis. So some numerical characteristic of my data. For instance, we might want to compare recovery times for old and new drugs. Then we find the p-value. Here's where the p-value comes into play. P-values reveal how likely your test results are if the null hypothesis were true. So if there was actually no difference between my drug and the existing drug, how likely would it be that I found this difference in recovery times? A small p-value suggests that the null hypothesis is unlikely. So it's unlikely that I would see this result if the null hypothesis were true. Based on that p-value, we're going to then make a decision. So a small p-value, usually less than 0.05, would lead us to reject the null in favor of the alternative. We're either going to reject the null or we're going to not reject the null. We never accept the alternative. So you can think of the p-value as a gauge of evidence against the null hypothesis. Smaller p-values mean stronger evidence. We set a significance level that we call alpha. Usually it's 0.05, and if the p-value is smaller, we reject the null. So let's make this crystal clear with an everyday example. Imagine we're doing a coin toss to decide who gets the bigger slice of pie. Tails you win, heads I win. You end up winning 3 times in a row. That's suspicious, right? We might suspect that that coin is biased. The null hypothesis would be that the coin is fair, equally likely to show heads or tails, and our alternative hypothesis would be that the coin is biased, that it's more likely to show tails. So we follow the same steps. First, we have to collect data. So we flip the coin many times and count the number of heads and tails. We calculate a test statistic based on that data. In this case, we look at the proportion of tails. So we get 70% tails when we flip the coin a lot of times. Then, based on our test statistic, we calculate a p-value. So if the coin was fair, how likely is it that we would see 70% tails? It gauges how our coin compares to fair ones. Then we make a decision. If we have a small p-value, it means we reject the null because it's evidence of bias in our coin. Let's zoom in closer on steps 3 and 4. Assume we have 1,000 fair coins, and we do a similar experiment with all of them. Flip them a bunch of times and calculate the percentage of flips that come up tails. If I plot the distribution of those results, it would look something like this. Most results would be close to 50% tails since the coin is fair, but the random nature of a coin flip means that there will be some variation. Not all experiments would give us exactly 50%. So how many of these fair coins give a percentage of tails that looks like the one from our data, 70%? And are any more extreme or closer to 100%? This is what our p-value shows us. We can count, estimate, or calculate the proportion of times we would see something at least as extreme. Once we have our p-value, we can use it to make a decision. Small p-values show that there's less chance of seeing something this extreme due to randomness in coins. So it's likely extreme or abnormal for a fair coin to get this percentage of tails. Usually we pick some cutoff called a significance level, and if p is less than it, we consider it small enough to be significant. This value is usually denoted as alpha and typically takes on values of 0.05 or 0.01. These numbers, however, have little mathematical significance. They're usually used as a rule of thumb, in part because of tradition. 0.05 was deemed small enough by a very prominent mathematician, R.A. Fisher. But however you choose your alpha, if p is less than alpha, we reject the null hypothesis. Notice that I didn't say we accept the alternative. Hypothesis testing gives us evidence, but not proof. It's much easier to prove that something is unlikely than to show that something is definitely true. And there you have it. Hypothesis testing and p-values are a dynamic duo of statistical decision-making. Remember that p-values quantify evidence against the null hypothesis. Smaller p-values signal stronger evidence that the null hypothesis is probably not correct and we're going to want to reject it. If this video clarified p-values and hypothesis testing for you, please don't forget to give it a thumbs up. It really helps my channel grow. And subscribe and hit the notification bell so you never miss another enlightening video. Also, if you have suggestions for more STEM content, drop them in the comments below and I'll do my best to create it for you. Thanks for joining me at Rosie STEM, and I'll see you in the next video. Bye.